Today's lesson is focused on something new, something called rational expressions. So let's start by just copying down these definitions here. Um, so go ahead and pause your screen, get these down, or listen through as I talk. Basically, rational expressions are going to be fractions that have variables involved, or fractions with polynomials. Um, and if you look, we got a couple examples here. We have 5k over 7. They can be simple, where we just have single terms on top and bottom, or they can be a little more complicated, where we have our second example here with a full-on quadratic on top divided by a binomial on the bottom. Either way, though, we're going to treat these exactly like we treat fractions, just with variables. So there's a few rules we'll go through today as we're working with them and over the next few days. The other kind of key definition for today is the word equivalent. This means expressions that work the same even though they look different. So if you look at the example below, we have 4x to the second power divided by 6x. Well, if you were to simplify that out, 4/6 can be written just like 2/3, right? Those are similar fractions or equivalent fractions. And same thing with the x's there, right? If you were to expand it out, x and x over on the left, just one x on the bottom, one set of those x's would cancel out and we'd be left with 2x to the third as our simplified kind of expression there. So that's something we're going to kind of go into more depth on through examples today, is working towards equivalent fractions. But those are our key definitions so far. So the skill that we're going to be working on today is rewriting expressions in lowest terms. And lowest terms is the same thing as simplest form. We're not changing anything about what the fractions or expressions mean. We are just finding a simpler way to represent them. So if you look here in example 1, we have 15 divided by 25x. Well, we can write that in simplest form or lowest terms by making sure that the top and bottom don't have any common factors. Now, some of you might be able to quickly work through this and just recognize that 15 divided by 25 works down to 3/5 as a fraction. But let's expand it out just so we can have a surefire way of getting there. We've gone through similar exercises with this factorization before, but I'm going to rewrite my fraction. I'm going to break down 15 to as small as factors as I can. And I know that this will be 5 times 3 is one way that I can rewrite 15. Then I also need to break down this bottom one, 25x, and I can do that with 5 times 5 times x. Once I have everything expanded out, I can start canceling out terms that show up on top and bottom. So we have a pair of 5s that show up on top and bottom. And that leaves me with 3 divided by 5x. And that is my expression in lowest terms. I can't bring this down any further. Okay, let's see this in example 2. And I would recommend that you start trying this on your own, pausing the screen once you see the new example pop up, and then checking your work as you go. I'll work through it and talk through it here. We have 4w to the third up top, so if I expand that out, I can get 2 times 2 times w times w times w. And on bottom, I can't break down 2 any further. There's no point in bringing it down to 1. I have 2 times w times w. And if I start crossing the common factors out, there's a 2 on top and bottom that we can cross out. We can cross out 2 w's each and be left with just 2w over basically nothing because we have everything crossed out. But when we do have everything crossed out, we can view it as being multiplied by 1 if we wanted to. And so we'd have 2w divided by 1, which can also be written as 2w because anything divided by 1 is just going to be itself. Okay, then moving on to example 3. Again, pause your screen if you want to try this yourself first. There's multiple variables involved, but we're going to handle this kind of the same way we've done before. A lot of you are probably recognizing that this is the same process we went through with division. So let's expand it out. If we think of 24 divided by 2, it'd give us 2 times 12. So we can go 2 times 2 times 2 times 3 times x times y. And we can also break down the 30. We'd have to go 2 times 5 times 3 to get us 30. And then we can expand out our x times x times x times y times y. And some of you won't need to expand this all the way out. You can recognize things that you can cancel on your own. But I find this is a helpful tool. So if we start canceling stuff out, we have a pair of 2's we can cancel. We have a pair of 3's we can cancel. And we have an x and a y. So that'll leave us with 4 up top. Without any variables, we'll have 5 on the bottom and x squared y as our denominator. There are 3 more examples we're going to go through, and these start to build in complexity a little more. You notice that we start having more complicated polynomials in example 4 here. And both these polynomials are written in factored form. And it's important to remember that when we're dealing with parentheses, we have to treat kind of everything within the parenthesis as its own factor. We can't cross out just the ones because they're pairs. We need to cancel out everything that is included in that parenthesis. So we have x plus 2 up top times x plus 1 divided by x plus 1 times x plus 3. Since that x plus 1 shows up on both levels of this, we can cross it out. We need to cross out that whole factor, everything within the parenthesis. And we can rewrite our final fraction as x plus 2 divided by x plus 3. And whether or not you include parentheses here or not is up to you. They are not needed because the whole phrase x plus 2 is written above that fraction without any sort of multiplication. Okay, go ahead and try this on your own with example 5. I will talk through it as well. We have x plus 3 up top divided by x minus 5 times x plus 3. And if we wanted to, we can think of this x plus 3 as having parentheses. That's up to you whether or not you want to think of it that way. But since it's not being multiplied by anything up top, we don't necessarily need them. Because that factor exists on top and bottom, we can cross it out. And we'll be left with x minus 5 on the bottom. But just like before in our previous examples, if we're not left with anything up top, we'll have a 1 up top, because 1 times anything is just going to be whatever that was. For a final example, a little more complicated here. We have x plus 2 up top divided by x squared plus 5x plus 6. You'll notice that we have standard form on the bottom, and we actually want to pull this into factored form first before we can do anything. So it's x squared plus 5s plus 6. Let's move it into factored form. We can use our cross puzzle. We'll have 6 up top, 5 on the bottom. We need to multiply to 6 and add to 5. So we'll get 2 and 3 as our numbers. So if we rewrite this fraction here, okay, we'll still have x plus 2 up top, but we will have x plus 2 times x plus 3 on the bottom. Then we can go through, we can make our cancellations. We see that x plus 2 exists on